Who of you are in Carlson's class? No, okay. Um, Specifically the reason I ask, this probably is somewhat applicable for students in Lee as well, is that I feel like neither of them assign very much homework. Looking at the problem, right, there's like maybe what, 6 or 7 problems like that. To me, that doesn't feel like enough practice. So if you're looking for more problems, I would highly recommend, if you're not already aware of it, checking out Grant's webpage, which I have bookmarked here. It looks like this. If you go down to the 21C part, there's lots of notes and stuff, but if you go all the way, scroll to the bottom, there are plenty of problem sets along with solutions. So if you're looking for more practice, also where you can look at the answers afterwards, that's a great place to find it because I would really, really, really strongly encourage you to do more practice because the amount of homework, at least that Carlson's assigning, to me just does not look like enough to have enough practice to learn the material. And probably also true for Lee. For Luli, I don't really know because he's doing it on the, I forget what you call it, but not WebWorks, the other one, which is not a bad platform, but it definitely feels like you get babies you through every step, kind of. So yeah, more practice is always good, right? You learn math. I think you learn math by doing math. So you got to do more math to learn the math. That said, what should we be talking about today? Where was I going? Not quite there yet. Where was I going? Not there yet. I think we're going to. Right. Yeah, yeah, yeah. So last time we had talked about the alternating series test, which is kind of important. Let's look at a few examples. So let's look at, say, for example, the Co-21C. Today's a fun date. 10/10. If you've had me for a class before, you might have heard me say this before, but I'll just remind everyone of an interesting fact that's not at all important. But all these days, April 4th, June 6th, August 8th, my birthday, 4/4, my brother's birthday, today, 10/10, and 12/12. This year they're all on a Friday. Next year they're all on a Saturday. Every year they're all on the same day of the week, whatever that day happens to be. Kind of neat. Anyway, that's all I want to say about that is that all those days are on the same day of the week. It's kind of interesting. They're called anchor days. Anyway, moving on with the actual math stuff. So some more examples with the alternating series test. So let's say, for example, we want to know about the convergence or divergence of the series from n equals 1 to infinity of -1 to the n plus 1 times n over n cubed plus 1. So typically when you're asked about whether or not a series is convergent, at some stage, probably at this stage, the question usually boils down to, does it converge absolutely, converge conditionally, or diverge? We only really phrase the question this way if it is an alternating series, because if it's a not alternating series, the question of conditional convergence is not applicable. So if it's an alternating series, you typically want to answer more this format, whether it's absolutely convergent, conditionally convergent, or divergent. So the flow chart of how you want to go through this is how it's written here. First, you want to check to see, is it absolutely convergent? So actually, what should I really do first though? The divergence test, but clearly it's going to pass, right? Or it's going to fail to be divergent by the test for divergence, right? The limit of this sequence is definitely 0. So absolute convergence, we're going to look at, say, does the series from n equals 1 to infinity of the absolute value of -1 to the n plus 1 times n over n cubed plus 1 converge or diverge? Now, I've probably written too much here, right? If you're doing the absolute value of an alternating thing, you're really just dropping the -1 to the n plus 1, the -1 to the n, right? Really, I should have just written this as the sum from n equals 1 to infinity of n over n cubed plus 1. And to my mind, we can say that that is going to be convergent by either the direct or limit comparison test. So this converges by the limit comparison test with the sum from n equals 1 to infinity of 1 over n squared. Let's do it. So limit as n goes to infinity of the unknown, and instead of dividing by the known, we're going to multiply by the reciprocal of the known, but that's just the limit as n goes to infinity of n cubed over n cubed plus 1, which is just 1. Since it's not infinity and not 0, they both have to have the same behavior. So since this converges, this also converges. Specifically here, since we were looking for convergence, we don't want the limit to be infinity. 0 would have been fine. So we're done with this problem. We don't have to do anything else. So what we would say is this series is absolute convergent. So the sum from n equals 1 to infinity of negative 1 to the n plus 1 times n over n cubed plus 1 is absolutely convergent. Yeah.
Yes.
Mm-hmm.
It's n over n plus 1.
Okay, n over n plus 1.
Yeah.
So, and it's alternating, right?
It's what?
Is it alternating?
Yeah, it's all.
So you're looking at something like the sum from n equals 1 to infinity of n over n plus 1 times negative 1 to the n plus 1.
Yes.
Okay. What's the first thing we should try? The divergence test. The divergence test, you can tell by the fact that I'm writing out, might tell us something here. If we look at the limit as n goes to infinity of n over n plus 1 times negative 1 to the n plus 1, although they don't even really know that part, that's not 0, right? Because this part goes to 1. So this is going to 1 times something that's alternating. So essentially my terms are getting closer and closer to 1 or negative 1, or 1 or negative 1, or 1 or negative 1. Diverges. We're done. So here, there really isn't anything else to do. It's certainly not absolutely convergent, because, and again, by the test for divergence as well. And then if you can't really apply the alternating series test here because again, it's failing to meet one of the criteria. Yeah. Now, more interestingly, if it was, say, the sum from n equals 1 to infinity of n over n squared plus 1 times negative 1 to the n plus 1, then this would certainly not necessarily diverge by the test for divergence. Or I should say, the test for divergence wouldn't show us anything. And then we would start looking at first absolute convergence. So the first question we ask is, does it absolutely converge? So we're looking at the sum. I'm going to write it the easier way this time, from n equals 1 to infinity of just n over n squared plus 1. And our intuition should tell us that this does not converge because it looks like or similar to 1 over n. And we know that the sum of 1 over n is divergent. Again, I don't want to even take the time to think about direct comparison here, right? This might be bigger than 1 over n. Maybe. I don't want to think that hard. I'm going to use limit comparison. So we're going to do limit comparison test with the sum from n equals 1 to infinity of 1 over n. And if we look at the limit as n goes to infinity of the unknown divided by the known, which is then just going to be the limit as n goes to infinity of n squared over n squared plus 1, we're going to get 1. And in this case, since we were trying to show what? What are we trying to show with this limit comparison test? What kind of thing are we comparing it against? Something that converges or diverges? This is famously divergent, right? It's like your best first example of a divergent series, typically. At least it's my go-to, right? If I'm trying to think of something to compare against to diverge, that's my first choice. So since we're limit comparing against something that diverges, we're going to show that this diverges as long as the limit isn't equal to what? Right, 0 is the problem here. Infinity would be fine. So I want to be extra careful here. This doesn't mean we get to say that our series diverges. All we can say is right now it is not absolutely convergent. So absolutely convergent? No. So then we're going to check to see if it's conditionally convergent by seeing if the original series passes the alternating series test. So now we're going to, on another piece of paper, because I should not try to write that in there, we're going to check, okay, how about the alternating series test for the sum from n equals 1 to infinity of n over n squared plus 1 times negative 1 to the n plus 1. So got to check three things. Thing one, is the non-alternating part positive? Definitely. As long as n is bigger than or equal to 1, which it certainly is, because it's starting at n equals 1. Second thing is the limit as n goes to infinity of n over n squared plus 1 equal to 0. Yes, it is. Which we already kind of knew because we already kind of would have done a check for the test for divergence. So typically, if your series isn't diverging by the test for divergence, then it's always going to pass this part of the alternating series test. And then the third part, which is the hardest part typically, is our sequence decreasing? I don't see a factorial, so I'm just going to use the usual method of taking the derivative of my function and showing that it's negative. So I'm going to say that f of x is equal to x over x squared plus 1, and the derivative is going to equal the bottom times the derivative of the top minus the top times the derivative of the bottom, all divided by the bottom squared. The great thing about doing this is the denominator is always going to be positive, so you only ever have to worry about the sign of the numerator. So this is going to end up being, let's see, x squared plus 1 minus 2x squared, which is just 1 minus x squared over x squared plus 1 squared. So this is definitely going to be negative as long as x is bigger than 1. So yes, n over n squared plus 1 is decreasing as long as n is bigger than 1. So we met all the conditions, which means that this series converges conditionally. I should say, this series converges by the alternating series test, and since it was not absolutely convergent, we say it is conditionally convergent. So this series, which always feels silly to write again, you probably don't need to write it again. I just feel like I should be, is conditionally convergent. All right, let's see. What else to say about this? Check one other thing here. Oh yeah, we should talk about that. So the other thing I wanted to point out is that, oh yeah, go ahead. Sure. Yeah, you can just put it down. I was just gonna say, all of it. Sure. The first page? Yeah. I will remind you, I do post the notes. So if a series is absolutely convergent, it is also convergent. Just as an FYI, right? So showing that the series converges absolutely means it's also convergent on its own. There is a way to prove that, but it's not really important. Yeah. Sorry, I was just remember I was looking at one of your so by the way, I finally added all the canvases, which is great. I was seeing that one of them had like this whole thing about like proving stuff with the contrapositive and by contradiction, and like, well, that's all well and good. It's not really like the purview of this class. So I'm sorry if you're being expected to do proofs with that, because in my opinion, that's more of like a Math 108 topic and like maybe 22A, but you shouldn't really be proving a lot of stuff in 21C. I don't remember what it was, either Carlson or Lully, because those are the ones I was looking at. There was like maybe it was something for the TA, but there was this whole handout on like on proof by contraposition and proof by contradiction. Probably Carlson. Yeah. So some people get a little too in the weeds about some of the stuff. Well, so there's one other thing to point out here, which is the alternating series remainder theorem. So let's look at this example. How many terms, and then we'll start talking about power series, are required to estimate the sum of the entire series to within, let's say, 0.0001. Well, it's not terrible at all if your series is alternating. So let's take a look here. Let's say, for example, we have the classic alternating harmonic series from n equals 1 to infinity of negative 1 to the n plus 1 times 1 over n. So this looks like, 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5, et cetera, et cetera, et cetera. So there's kind of this great thing about alternating series that, well, in fact, I should probably say a little more here. So the reason you can kind of, oh my God, the words coming out of my mouth. If you have shown that your alternating series converges by the alternating series test. So, right, so again, just as a quick aside here, if your terms are getting smaller, so your AN is smaller than the next, no, it's bigger than your AN plus 1 is smaller than the previous term. So if your terms are getting smaller and the limit of your terms is 0, you might have seen this picture already, but it's worth contemplating. So I'm going to find the sum graphically. So I'm going to first say, add up my first term, which is a sub 1. And then I'm going to subtract my next term, which is smaller. So my first partial sum is S1. And if I subtract my next value, well, it can't take me back as far as I started. So if I subtract A2, I'm going to end up with a new partial sum that's somewhere right there. And if I add the next term, which is smaller than the previous term, so I add A3, I can't quite get back to where I was before. So we're going to keep zeroing in on what our actual sum is. Right, so we're stuck somewhere in here. So that's kind of how we're actually showing this convergence, right? Is essentially you're bounded and you're monotonic, so you have to converge. Monotonic? You're certainly bounded. Monotonic might not be quite the right thing to say here. Yeah, but it definitely does converge because you're zeroing in on some spot that you can't get away from. What this means is that's also true for like the leftover bits. So, for example, if we take our series here and go out to say like 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus 1/6 plus all the way to say 1 over what's the number I want here? 1/10, 1/100th, 1,000th, 1/10,000th to minus 1 over 10,000 plus 1 over 10,001 and so on. Right? All of this part over here, that's going to be less than or equal to the absolute value of the first term. Because essentially, and unfortunately I've got the wrong, the sign I would prefer not to have, but if we look over here for a second, right, you've got 1 over 10,001 minus something smaller, plus something a little bit smaller, minus something a little bit smaller. So whatever all those terms add up to has to be less than or equal to whatever the first term is. So essentially you can say for some alternating series, the remainder is less than or equal to the first term in the beginning of the remainder. So essentially we can say that the remainder after the first n terms is less than or equal to the absolute value of the n plus 1 term. Which then makes it really easy to answer this question. Because we say, well, great, we want our remainder to be less than or equal to 0.0001, which is 1 over 10,000. And we just pick our n to be 9,999. So we know we need n equal to 9,999 terms to have the approximation we're looking for. Now, it's still not nice to calculate, right? Adding up the first 9,999 terms of this is not fun for a human to do without a computer. But that's the idea, is that you can certainly approximate this to whatever degree you like by using the number of terms you need. Yeah. Yes, yes. Let me say more about that. So if you're writing out some infinite sum from n equals 1 to infinity, a sub n, so it's, a1 plus a2 plus a3 plus all the way to some nth term plus some n plus 1 term plus some n plus 2 term, and so on forever. So these first n terms are nth partial sum. So I say this is like my Sn, the sum of the first n terms, and these remaining terms are the remainder of the first n after you added the first n terms together. So it always kind of was funky to me because like the remainder starts at the n plus 1 term for r, like the Rn remainder starts at n plus 1, but that's just the way the notation works. So Sn, sum of the first n terms, Rn, the remainder after summing the first n terms, or the leftovers. So another way to think about this is that this would be your approximation of your value, and this would be your error. And so for an alternating series, which is going to be A1 minus A2 plus A3 minus A4, et cetera, et cetera, et cetera, all the way to, plus -1 to the n plus 1 times A sub n plus -1 to the n plus 2 times A sub n plus 1 plus so on, so on, so on. These first n terms are your partial sum or your estimate, and these remaining terms are your remainder. And here we can say that the remainder is less than or equal to the absolute value of just the first term of the remainder, even though there's lots more terms that you're adding together here because of the nature of this back and forth, getting smaller and smaller, zeroing in some value. So that's the nice version of this idea, that you can estimate your error by just taking the first term of the sum of all the error terms. Now, I want to emphasize here, this is only true for an alternating series. Later on, we're going to learn about a different way to estimate the error if your series is not alternating, and it's a much bigger pain in the butt. But sometimes it's all you've got. But I would say very generally, if you're looking for estimating the error of a series, try to hope that your series is alternating, because that's often what people are going to go to because it's just easier for everybody. Doesn't mean it's going to be what's happening all the time, though. All right, yeah. Mhm. Yeah, all right, so let's look at power series. So this is where we start writing, instead of just sums of a bunch of numbers, sums of a bunch of variables, a bunch of powers of x. So, for example, well, we know how geometric series work, right? We know that, say, for example, 9 plus 3 plus 1 plus 1/3 plus 1/9 plus 1/27 forever and ever and ever. That's a geometric series, right? Every time to get from one term to the next, we're multiplying by 1/3. So our ratio is 1/3. And definitely this geometric series adds up to the first term divided by 1 minus the ratio, which in this case is 9 divided by 2/3, which is 27/2. And that's kind of true as long as your ratio is between -1 and 1. So why don't you all try answering this next question? What does 8 minus 4 plus 2 minus 1 plus 1/2 minus 1/4 What's that going to add up to? Well, let's see. It's going to be my first term over 1 minus my ratio. What's my first term? It's the first, right? It's the first thing we wrote. It's 8. And my ratio here is negative 1/2, right? Every time we're multiplying by negative 1/2 to get to the next thing. So here we've got 8 divided by 3 over 2, which is 16 over 3. But a more interesting question to ask is, can we find a series that adds up to 10? Well, yes, definitely. In fact, you can probably find lots of different ones. So we can do this in a number of ways. Let's try to make our lives easy though. So here's what I really want to do. I'm going to write out my terms, but not. And I know I want this to equal, well, it's going to equal the first term divided by 1 minus the ratio. I want that to equal 10. So an easy way to get to 10 is like 5 times 2, or 5 divided by 1/2. So I would really like this to be, the first term to be 5, and the 1 minus r to equal 1/2, which means r would also be 1/2. So it looks like if I do 5 plus 5 over 2 plus 5 over 4 plus 5 over 8, and so on and so on, that should add up to that. And we could even, and I have been kind of avoiding, not avoiding, you could definitely write this as a series, right? I mean, you could write it more compact. Technically, it's written as a series, right? This infinite sum is a series, but you could write it using the summation notation. You could definitely write this as the sum from n equals 1 to infinity of 5 times 1/2 to the n minus 1. Or you could write it as the sum from n equals 0 to infinity of 5 times 1/2 to the n. Or literally 1,000 other ways that would be just as good, but these are kind of the usual ways. So where are we going with this? Well, we would like to find an infinite series that adds up to a function. So instead of adding numbers together, we're going to say, well, what if we did 1 plus x squared plus x cubed plus x to the fourth, and so on forever, which would be the sum from n equals 0 to infinity of x to the nth power. Well, it's still geometric. My first term is 1, and my ratio is x. Every time we are multiplying by x. So our sum is 1 over 1 minus x, provided that our ratio still lives in the right boundary region, provided that x is between -1 and 1, right? That a geometric series only converges to its value if your ratio is between -1 and 1. So here we can say that this infinite series is equal to this function as long for values of x that are between -1 and 1, or the absolute value of x has to be less than 1. And we call that the interval of convergence. So we would say that, okay, this power series, the sum from n equals 0 of x to the n, converges to the function f of x equal to 1 over 1 minus x on the interval from -1 to 1 exclusive. And that right there is called the interval of convergence. Okay. Yeah, we got that. Okay, we got that. So one thing we do, I will say, we use this particular example and idea a lot to deal with other series. So let me show you another example. Let's say I want to know, I want to find a series for a power series for the function f of x equal to x over 1 minus x squared. So here's what we're going to do. We're going to manipulate this. We know that 1 over 1 minus x is equal to 1 plus x squared plus x cubed, and so on and so on and so on forever. So I'm going to try to manipulate each side of this equation by using substitution and multiplication. So I really, really, really would prefer to have, instead of 1 over 1 minus x, 1 over 1 minus x squared. So when you think about this, I wouldn't think of this as x really. Like what I really have here is 1 over 1 minus whatever I want to have there equal to 1 plus whatever is in the parentheses plus whatever's in the parentheses squared plus whatever's in there cubed and so on and so on and so on. So we can put anything inside those parentheses, and I want to put x squared inside those parentheses. So we can say that for sure 1 over 1 minus x squared is equal to 1 plus x squared plus x squared squared plus x squared cubed and so on and so on. Provided that our ratio, our thing that's in the parentheses, has an absolute value that's less than 1. And now we're almost there. We just have to multiply both sides by x. So then we can say that x over 1 minus x squared is equal to x plus x cubed plus x to the fourth plus x to the, plus x to the what? To the fifth plus x to the seventh. And that's equal to the sum from n equals 0 to infinity of x to the 2n plus 1. As long as, now we can work on this a little bit. If x squared is less than 1, x has to be between -1 and 1. So this is really the same as saying that the absolute value of x is less than 1. So people do this a lot, meaning they give you a function and they say, okay, well, write this function as a series, and we kind of our first line of attack is to see how can we manipulate this geometric idea that if you just add up a bunch of things where you just multiply the same thing every time, you get 1 over 1 minus that ratio. Or I should say, whatever the first term is over 1 minus that ratio. That's what we're doing here. Literally, right? First term, x. Wow, I could have been smarter about that. So I feel like I might have worked too hard here to do this. Because if I had really thought about this a lot, oh no, wait, right? I could have just said, look, my first term should be x, my ratio should be x squared. So I could have said, well, if my first term is x, and my ratio is x squared, then it's going to be x plus x squared times x plus x squared times x cubed plus and so on and so on and so on. That's a much I mean I feel like that might be a weird way to think about it, but it definitely makes sense saying the words out loud. If we know that your geometric thing adds up to the first term divided by 1 minus the ratio, then you can just look at it as the first term on top of a 1 minus the ratio on the bottom. As long as it's in this format, right? But that's not always going to be the case. Let's look at some other examples here. Sure. Yeah. So, yeah. So let's say we have something like, sure, I want this. So let's find a series for the natural log of 1 plus x. And now we are very much in a different place. Right? It does not look like 1 over 1 minus some ratio. One thing we often do with these is we can differentiate or integrate as we like. So what we're going to do first is we're going to differentiate that to get something that looks familiar. So the derivative of the natural log of 1 plus x is 1 over 1 plus x, which I'm going to write in a more specific way. I'm going to write it as 1 over 1 minus negative x. And now I'm going to be clever like I was before, kind of, and say, well, cool. I've got 1 over 1 minus my ratio, or I should say my first term over 1 minus my ratio. So that should just be my first term plus my ratio times my first term plus my ratio times my second term, and so on. So this is looking like 1 minus x plus x squared minus x cubed plus x to the fourth, and so on, minus x to the fifth. Now we're not done, because that's not the infinite series or the power series for the natural log of 1 plus x. That's the infinite series for the derivative of the natural log of 1 plus x. So to get back the series we actually want, we have to anti-differentiate the thing we just found. So we can then say that the natural log of x is equal to the antiderivative of all this. Now, we could write that all out, but I'm actually going to show you something else instead. I'm going to write this as the sum from n equals 1 to infinity. And although we could write it, from n equals 0 to infinity, we could write it as negative x to the nth power, but I think it's better to kind of separate as much as you can away from the x. So it's going to be better to write this as negative 1 to the n times x to the n. And now we're going to try to integrate that. Wow, can I write that? Sure. We're going to do the integral of the sum of negative 1 to the n times x to the n. And kind of the cool thing here is that you can essentially pass the integration through the summation, right? Whether you add up a bunch of things first and then integrate them all, or integrate each thing first and then add them all up, we should still get the same result. So we can rewrite this as the sum from n equals 0 to infinity of negative 1 to the n, which doesn't have a variable in it, so it's not going to change at all, times the antiderivative of x to the n dx. Right, that's in our sum. And then the antiderivative of x to the n is just x to the n plus 1 over n plus 1. So that's going to be the sum from n equals 0 to infinity of negative 1 to the n times x to the n plus 1 over n plus 1. Let's write out the terms to see if they actually are what we think they should be. So we plug in 0, we get 1 times x to the first over 1. We plug in 2, plug in 1, we get negative 1 times x to the second over 2. And then we're going to get plus x to the third over 3, and then minus x to the fourth over 4. Which is exactly what the antiderivative of each of these terms would give us. Right? The integral of 1 is x, the integral of negative x is negative x over 2, and so on and so on and so on. So it is really kind of nice that you can push integration through a summation without issue, typically. So, there's something else I want to say here. No, I don't forget about that. Okay. Yeah. So here's what I wanted to point out. I want to say this the right way. What time have we got? Okay. When you integrate or differentiate a series, that doesn't change the radius of convergence, which I know we haven't talked about yet. So let me go back to this previous example for one moment here. So this series, its interval of convergence was from negative 1 to 1. What's the center of that interval? 0. That's the center of this series. When I think about the center, I think of it as the value that if you plug that value in, essentially all the terms would become 0, except for maybe the first term. We'll show another example where it's a little more obvious. So the center of this series is 0. And how far is it from 0 to either side? 1. The radius is 1. So the radius of convergence is 1. And the radius of convergence isn't affected by integration or differentiation. There's a nice proof of it that's pretty easy to show, but we'll wait. But on the other hand, the interval might change because the endpoints, you might not get convergence or divergence anymore depending on what's happening. Or you might, where you wouldn't have before. So I'll point out that, going back to this other example here, this series, this function, the series for this function, is definitely geometric. And geometric series don't ever converge to their endpoints. So certainly 1 over 1 minus x, the interval of convergence is negative x, absolute value is less than 1, which just becomes x being strictly between negative 1 and 1. On the other hand, this series here might have different things happening at the endpoints. So what do we do? Well, let's ask ourselves the question. Does this series converge if x is equal to positive 1? Well, if I plug in 1 for x, I get the sum from n equals 0 to infinity of negative 1 to the n times 1 to the n plus 1 doesn't do anything, right? 1 to any power is just 1. So you've got negative 1 to the n over n plus 1. So does this series converge or diverge? Well, it's an alternating series. And if you apply the alternating series test, it would meet all the conditions. The limit of the sequence is 0. The terms decrease. They all start off positive. They're not alternating. So yes, it does. On the other side of things, what if x is equal to negative 1, the other endpoint of our interval? Well, if x is negative 1, it's actually not going to converge. Because if x is negative 1, you're going to have negative 1 to the n times negative 1 to the n plus 1. So you're going to have the sum of negative 1 to the n plus 1 is 2n plus 1 over n plus 1. And negative 1 to the 2n plus 1 is always negative 1. Right? You have negative 1 to an odd number every time. So that's just going to be the sum of negative 1 over n plus 1, which diverges. Right? It's like the harmonic series, but the negative of it. So here, the interval of convergence includes positive 1, but excludes negative 1. So it's negative 1 to positive 1. Now, if you look back to your original function, that would make a lot of sense. But negative 1 would be a problem for that function. Yeah, negative 1 is a huge problem for that function, right? If you plug in negative 1, you get natural log of 0, which is undefined. So typically, right, your interval of convergence shouldn't include any points where your function would be undefined. It also excludes a lot of other points, right? This function certainly would be defined if x was, 2 or 3 or 4 or 5, but this infinite expression for it won't converge on those values. Okay. So where do we go with this? Typically, we go to looking at power series and talking about finding their interval and radius of convergence. So let's look at something like, where'd you go there? Yeah. So for example, let's say we had something to the effect of, sorry, I'm not looking. Yeah, there we go. Let's say we have the sum from n equals 1 to infinity of x minus 3 to the nth power over n to the fourth times 2 to the n plus 1. We want to know what is the interval of convergence for this power series. I don't really want to write out the whole series or the whole no, yeah, I don't want to yeah, there's no need to write out the whole series here. So we want to know for what values of x does this converge? Well, the typical way of dealing with this is by applying the ratio test. So we're going to use the ratio test. So we're going to take the limit as n goes to infinity of our an plus 1 over an term. And here the absolute values are especially necessary. We're going to write this as the limit as n goes to infinity of the absolute value of our n plus 1 terms. That's going to be x minus 3 to the n plus 1 over n plus 1 to the fourth times 2 to the n plus 1 is n plus 2. And then instead of dividing by an, we're going to multiply by the reciprocal of an. So that's going to be n to the fourth times 2 to the n plus 1 over x minus 3 to the n. We're going to group together the similar things. So it's going to be the limit as n goes to infinity. Let's see, we have the absolute value of x minus 3 to the n plus 1 over x minus 3 to the n. We have n to the fourth over n plus 1 to the fourth. And we have 2 to the n plus 1 over 2 to the n plus 2. And The only part where we actually need the limit is for this part right here. The limit of this part is going to be 1 because it's n to the fourth over n to the fourth plus smaller powers of n. You don't even need the limit for these parts because those parts just simplify. So we end up getting the absolute value of x minus 3 over 2, right? Because 2 to the n plus 1 over 2 to the n plus 2, this is just going to be 1/2. This is just going to be x minus 3. Okay, so that's what our limit's equal to. And we know that the ratio test tells us that if that limit is less than 1, the series converges. So we're going to say that this is less than 1, and then we're going to find the interval values for x that make it converge. So we're going to solve this inequality. So I'm going to have the absolute value. No, actually, I don't. I'm going to say just x minus 3 divided by 2 is between 1 and -1. Multiply all sides by 2. So -2 is less than x minus 3 is less than 2. Add 3 to all sides. 1 is less than x is less than 5. My center is 3. And you can see that in one of two ways. It's literally the middle of 1 and 5. But if you go back to the very beginning, if you plug in x equal to 3, not almost, all the terms will be 0. Right? Because 3 minus 3 to the first is 0, and 3 minus 3 to the second is 0, and 3 minus 3 to the third is 0. Doesn't matter what you have going on. If x is 3, you're just going to get 0 plus 0 plus 0 plus 0 plus 0. A series always converges at its center. Because if you plug in the center, you're just going to get an infinite sum of zeros. Maybe one non-zero term at the beginning. So the center is 0. Sorry, the center is what? Center is 3. And the radius, you can either think of as the distance from the center to either endpoint, or as half the total interval, or half the diameter of convergence is what I often call it, because it's twice the radius. So the diameter of convergence is 5 minus 1, which is 4, and the radius of convergence is 4 divided by 2, which is 2. One way people often think about it is when you're setting up this inequality, whatever x is being multiplied by, it's the reciprocal of that. It's the absolute value of the reciprocal of that. So here x is being multiplied by 1/2, and the radius is the reciprocal of 1/2, which is 2. That's a true thing as well. That's one way people like to kind of see it. I don't love it personally. But we're not done because the interval of convergence, well, the problem is we don't know what's happening at 1 and 5. Because, I'll say one more thing. We know that the ratio test tells us that if this limit is less than 1, you get divergence. If this limit is bigger than 1, whoa. If this limit is less than 1, you get convergence. If the limit is larger than 1, you get divergence. But if the limit is equal to 1, what do we know? Nothing. If the limit is equal to 1, it could converge or diverge. And the problem here is that if x is equal to 5, 5 minus 3 divided by 2 is 1. If x equals 1, 1 minus 3 divided by 2 is -1, and then the absolute value is 1. So at the endpoints, the ratio test is inconclusive. And so you have to go back and test those endpoints. So if we look back at the original thing and we test these endpoints, why am I trying to squeeze things in? I've got lots of paper. So if we go back and plug in, say, x equal to 5, we have the sum from n equals 1 to infinity of 5 minus 3 to the n. I know it's 4 o'clock, so we'll wrap this up over n to the fourth times 2 to the n plus 1. If you look at that, it's going to be the sum from n equals 1 to infinity. 2 to the n over 2 to the n plus 1 just gives you a 1 over 2. So it's 1 over 2n to the fourth. Definitely convergent. And similarly, if you plug in 1, typically what happens here is you plug in one of them and it's not alternating, you plug in the other one, it is alternating. So if the not alternating one converges, the alternating one is for sure going to converge. So I would always encourage you to try to check the one that's not alternating first. So if you plug in x equals 1, you get 1 minus 3 to the nth power over n to the fourth times. I'm going to break this up as 2 to the n times 2, and then you have the sum from n equals 1 to infinity of -2 to the n over 2 to the n times 1 over n to the fourth times 2. And negative 2 to the n over 2 to the n is just negative 1 to the n. So we really have the same series as here, except it's alternating. You have negative 1 to the n times 1 over 2 times n to the fourth. But if this converges, this has to converge because it's absolute. So this also converges. So here our interval of convergence would have been bracket 1 to bracket 5, including both endpoints. And really anything can happen at the endpoints. You can have both of them give convergence, both of them give divergence, or one give the convergence and one give divergence. So you always have to check both. All right, I stopped there. It's 4:01.